Welcome back to the deep dive. We spent a lot of time on this show talking about the shiny exterior of AI.
Yeah, the output,
Yeah.
the art, the code, all of that.
Exactly. We marvel at the bar exams it passes.
Yeah,
But tonight, I want to do something different. We are going to pop the hood.
it's about time, honestly.
Yeah.
Because the exterior is fascinating, but the engine.
Yeah.
The engine is where the actual revolution is happening.
Right. And this has been a bit of a black box for me personally, and probably for a lot of you
Oh,
listeners.
absolutely. It's opaque by design sometimes.
We've covered neural networks before. We know they have layers and neurons.
The weights, the biases.
Right, the anatomy. That is the body. But a body without a mind is just a statue. So how does this pile of digital neurons actually learn anything?
That is the fundamental question. Because structure doesn't equal intelligence.
Okay.
You can build a network with 1 trillion connections, but if you don't know how to tune them, it's just a random noise generator.
Yeah. And the scale here is what terrifies me. Like, if I'm writing a standard software program, I write the logic. I tell the computer, if X, then Y.
Traditional deterministic programming.
Exactly. But in a neural network, nobody writes the logic. The logic lives in these billions of parameters, these little knobs.
Billions of them.
And somehow, we have to figure out how to twist every single one of them just right so that the machine stops outputting gibberish and starts outputting Shakespeare.
It sounds impossible when you put it that way.
It feels impossible. I mean, if you have 1 billion knobs and you don't know what any of them do, how do you even begin? You can't just guess.
No, you can't guess. If you tried to guess the settings for a modern neural network, you would be guessing until the heat death of the universe.
Wow.
We need a map. We need a guide. And that guide is an algorithm called backpropagation.
Backpropagation. It sounds like something from a sci-fi horror movie.
It does.
But I know it's basically the bedrock of modern AI.
It is the single most important algorithm in computer science history.
Really? The single most important.
I don't say that lightly. Without backprop, there is no ChatGPT, no Midjourney, no self-driving cars.
It's the engine.
It is the engine that drives the learning process. And while the math relies on calculus, the intuition is surprisingly physical.
Okay, so let's get physical. I was reading through the research you sent over, and there's this recurring analogy of a landscape, a mountain range.
Right. This is the best way to visualize what the computer is doing. I want you to imagine you are standing on a massive, rugged mountain range.
Okay, I'm there.
There are peaks, valleys, ridges, plateaus. It's totally chaotic.
And the goal here is to find the lowest point, right? The deepest valley.
Exactly. In this analogy, altitude represents error.
Okay, error.
The higher up you are, the stupider your model is. If you're on the highest peak, your AI is predicting that a cat is a toaster.
Right.
If you're in the lowest valley, your AI is perfect. So your mission is simple, get to the bottom.
Simple enough. I look down, I see the valley, and I walk there.
But here's the catch. You are blindfolded.
Of course I am, because why make it easy?
Exactly.
Yeah.
You cannot see the horizon. You cannot see the peaks. You can't even see your own feet. You have absolutely no map of the terrain.
Okay.
All you have is the ability to feel the slope of the ground directly beneath the soles of your shoes.
So I'm standing on a mountain, blindfolded, trying to find the lowest point in the world. This sounds like a recipe for falling off a cliff.
It really does. But think about it. Even if you're blindfolded, if you feel the ground slipping down to your left, what do?
I take a step to the left.
Precisely. And then you stop. You feel the ground again.
Right.
Maybe now it slopes slightly forward. So you take a step forward.
Yeah, I just keep doing that.
If you repeat this process,
Yeah.
measure the slope, take a step, measure the slope, take a step eventually, gravity does the work,
Yeah.
you will end up at the bottom.
This is what you call gradient descent.
That is the algorithm.
Yeah.
Gradient is just a fancy math word for slope.
Slope, right.
And descent means going down. You are descending the slope.
Here's where I have to push back, though, because that sounds way too simple. If I'm hiking in the real world and I just blindly follow the slope downhill, I don't necessarily end up at the bottom of the mountain.
No, you don't.
I might end up in a ditch, or a pothole, or a little valley that's still 5,000 feet up.
You're talking about local minima. The fake valleys.
Right. If I get stuck in a bowl halfway down the mountain, I'm trapped. Every direction is up, so my algorithm tells me to stop. But I'm not at the bottom.
This was actually a huge fear in the early days of AI.
Really?
Yes. Researchers thought these high-dimensional landscapes would be full of traps. They thought we'd never find the true solution.
So why doesn't GPT-4 get stuck in a pothole?
Because of the dimensions.
Ah.
And this is the part that is really hard to wrap your head around.
Try me.
In our hiking analogy, we are in 3D space. You can move north-south or east-west. It's easy to get trapped in a hole in 2 dimensions.
Right, a literal bowl.
But the neural network isn't in 3D.
No. The source material mentions that GPT-3 has 175 billion parameters.
Which means, in our analogy, you are hiking on a mountain range that exists in 175 billion dimensions.
I can't even picture 4 dimensions, let alone billions.
Nobody can. But here's the mathematical magic. In 175 billion dimensions, it is incredibly hard to get stuck.
Why?
To be in a true trap, the ground would have to slope up in every single one of those billions of directions simultaneously.
Oh, I see.
Yeah.
So even if I'm at the bottom of a bowl in a million dimensions, there's probably at least one other dimension where the ground is still sloping down.
Exactly. There is almost always an escape route. We call these saddle points rather than traps.
Like a horse saddle.
Yes, it goes up in front and back, but down on the sides. You just slide off the side.
That is surprisingly comforting. We aren't smart enough to navigate the maze, so we just made the maze so big that there aren't any dead ends.
That's a great way to look at it. The sheer scale of the space actually makes it easier to find a path down.
Okay, so we know the strategy, walk downhill,
Yep.
but we need to translate this back to the computer. In the analogy, I have feet to feel the slope. The computer just has data. How does it feel the ground?
To understand that, we have to look at the life cycle of a training step.
Okay.
It starts with the forward pass. This is what the neural network actually does.
The prediction part.
Think of it like a massive system of water pipes. The water is your data.
Okay, water is data.
It flows in at the top. It passes through layers of pipes, valves, and filters. The valves are your parameters, the weights. They control the flow.
So if I'm training a model to identify photos, I pour the pixels in the top.
Yep.
The water rushes through these billions of valves and eventually comes out of a spout at the bottom labeled cat or dog.
Exactly. But here is the crucial moment. Let's say you pour in a picture of a cat.
Okay.
The water flows through, and it comes out of the spout labeled dog.
The model is wrong. It failed.
It failed. But we need to be specific about how much it failed. We can't just say bad robot. We need a number.
Right.
This is where the loss function comes in.
The loss function, this is essentially the scorecard.
It's more like a penalty score. If the model says it's a 100% chance this is a dog, and it was actually a cat, the loss function calculates a number that represents that error.
Like getting an F on a test, but the F is a number like 2.5 or 0.003?
Exactly. If you're doing regression, like predicting house prices, you might use mean squared error.
Mean squared error?
Right. If you predict $200,000 and the house is actually $500,000, you square that difference. That massive number is your loss.
Squaring it really penalizes the big mistakes.
Huge penalty for being way off. Or for classification, you use cross-entropy loss. But the concept is the same.
So the entire goal of training is just make this number smaller.
That is the game. Minimize the loss, walk downhill. But now we have a problem.
Which is?
We have this one number. Let's say our loss is 5.0. That's high. We know we messed up.
Okay.
But we have 175 billion valves that the water flowed through. Which one caused the problem?
Right. It's a classic whodunit. We have a body in the library. The error.
The error.
And billions of suspects. Did the valve in the first layer screw up? Or the one in the 50th layer? Or was it a combination of a million valves just being slightly off?
This is the central problem that backpropagation solves. It is the detective that interrogates the network.
Okay.
And it does it using the chain rule from calculus.
The chain rule. Now, don't glaze over. I know calculus triggers a fight or flight response for some people, but the concept here is actually really intuitive.
It really is. Imagine a Rube Goldberg machine.
Oh, I love those.
Right, those complex contraptions. A ball rolls down a ramp, hits a lever, tips a bucket, pulls a string, and flips a switch.
Okay, I'm visualizing it.
Now imagine the switch didn't flip all the way. You have an error at the end.
The loss.
Yes. You want to fix it by moving the ramp at the very beginning.
But the ramp isn't touching the switch. It's separated by 5 other things.
Exactly. So you have to trace the influence backward.
Backward.
You ask, how does the switch depend on the string? Then, how does the string depend on the bucket? Then how does the bucket depend on the lever?
It's a chain of blame.
A chain of influence.
Sure.
If you know how A affects B and how B affects C feel, you can mathematically determine how A affects C.
You just multiply the links together.
Exactly.
So backpropagation is basically starting at the end, at the loss, and working backward through the layers, calculating exactly how much each neuron contributed to the mistake.
Precisely. We go to the output layer and say, hey, you were a little off. How much should we nudge you?
Right.
Then we move to the layer before that. Hey, how much was your fault? And we keep multiplying these sensitivities all the way back to the input.
Hence backpropagation. We are propagating the error backward.
By the time we reach the start, we have a very specific number for every single weight in the network.
Every single one of the billions of knobs.
All of them. And we call this number the gradient.
Let's define that clearly. The gradient is the instruction manual for the next step.
Yes. For every knob, the gradient tells us two things: direction and magnitude.
So direction is turn this knob left or right.
And magnitude is turn it a tiny bit or crank it hard.
It tells us which way it tilts the ground downhill for that specific dimension.
Exactly. So now we have the map. We know exactly how to tweak all those billions of knobs to make the error just a tiny bit smaller.
So we do it. We update the weights.
We do.
And this brings us to the engineer's toolkit. Because having the map is one thing, but actually taking the step is another.
Very true.
And I know there's a parameter here that drives engineers crazy. The learning rate.
The learning rate. This is the Goldilocks parameter.
Yeah.
It controls how big of a step you take down the mountain.
Why does the size matter? If I know the direction is down, shouldn't I just run?
Imagine our blindfolded hiker again. The gradient says the slope goes down to the left.
Okay.
If you take a massive leap, say 100 meters, you might jump right over the valley and land on the next mountain peak.
You overshoot, the error actually gets worse.
It explodes. We call it exploding gradients.
Mm-hmm.
Yikes. But if you take a tiny microscopic step, like a millimeter, you will make progress, but it will take you 10,000 years to reach the bottom.
So you need a step size that is just right.
Which is really hard to find manually.
Yeah.
That's why modern AI doesn't rely on a fixed step size. We use optimizers.
Optimizers. The most famous one is called ADAM. I see this name in every paper. Who is ADAM?
ADAM stands for Adaptive Moment Estimation.
Ah, an acronym.
Think of Adam as a very intelligent hiker. He doesn't just take the same size step every time. He looks at the terrain.
He adapts.
Yes. If the slope is smooth and steady, Adam gains momentum. He takes bigger strides to move fast.
Makes sense.
But if the terrain gets rocky and chaotic, if the gradient is bouncing around, Adam slows down.
He takes careful, small steps to avoid falling.
Exactly. So the optimizer handles the walking speed.
But there's still a huge bottleneck here, right? We're talking about massive data sets. If I have to run 1 billion images through the network just to calculate one step,
That's the computational bottleneck. In pure gradient descent, to know the exact slope, you have to check every single data point you have.
that sounds slow.
It's like polling every single person in the country before making a decision. It's highly accurate, but it takes forever.
So we compromise, we use batches.
Any batch gradient descent. Instead of checking 1 billion images, we grab a random handful, say 64 images.
Okay.
We calculate the loss for those 64, find the slope, and take a step.
But isn't that a bit sloppy? 64 images might not represent the true average. The slope could be wrong.
It is noisy. The path down the mountain isn't a straight line anymore. It's more of a drunken stumble.
A drunken stumble.
But here is the fascinating thing about AI. That noise is actually good for us.
Good. How is inaccuracy good?
Remember those small potholes? The local minima?
Right, the fake valleys.
If you follow the slope perfectly, you slide right into the first pothole and stop.
Because perfect math says you're at the bottom.
But if you're stumbling around because your batch was noisy, you might accidentally stumble out of the pothole and keep going toward the real valley.
So the drunken stumble stops us from settling for a mediocre solution.
Exactly. It adds just enough randomness to keep the exploration alive.
That's brilliant.
Plus, computer hardware loves batches. GPUs are designed to process 64 or 128 things at once. It's structurally efficient.
Okay, so we have the engine, we have the fuel lines, but this story isn't all smooth sailing.
No, definitely not.
I want to talk about the AI winter, because for a long time, backpropagation simply didn't work for deep networks.
It really didn't.
We could train shallow ones, but as soon as we added more layers, the whole thing just stalled out.
This is the vanishing gradient problem.
Yeah.
And it kept the field frozen for nearly 2 decades.
What exactly was happening? We had the math, we had the chain rule. Why did it break?
It goes back to the chain rule. Remember, to find the blame for the first layer, you have to multiply the sensitivities of all the layers after it. You are multiplying a long chain of numbers.
And often, those numbers are small. Decimals.
Right. Think about elementary math. What happens if you take 0.5 and multiply it by 0.5?
You get 0.25, it gets smaller.
And if you multiply that by 0.5 again and again, 50 times.
It effectively becomes zero.
Exactly. So imagine the telephone game.
Okay.
You whisper a message at the output. By the time that message passes through 50 layers of multiplication to reach the input, the signal is totally gone.
It's silence.
Silence. So the back of the network, the part responsible for basic features like edges and textures, never gets the update signal.
It never learns.
The gradients vanish. The engine is running, but the wheels aren't turning.
And this problem seemed insurmountable for years.
It did. People gave up on deep networks entirely.
So how did we solve it? Because obviously we have deep learning now.
A combination of better engineering.
Like what?
We changed the activation functions,
Yeah.
the filters in the pipes, to things like ReLU, which don't shrink the numbers as much. But the big breakthrough, especially for the massive models we see today, was the residual connection.
This is the res in ResNet.
Yes. It's an incredibly simple idea. Imagine in our telephone game, instead of just whispering to the next person, you also pass a written note that skips over the next person and goes directly to the person after.
A shortcut.
A skip connection.
Ah.
It allows the gradient to flow through the network along a superhighway, bypassing the multiplication chain.
Wow.
It keeps the signal loud and clear, even if the network is 1,000 layers deep.
It's wild to me that something that sounds like a minor tweak, just add a shortcut, is the reason we have GPT-4 and not just a slightly better spell checker.
It's often the simple architectural shifts that unlock the math.
Now, before we wrap up, I want to pivot to the developers listening.
Sure.
Because we've been talking about calculus and gradients and chain rules. If I'm a software engineer and I want to build a model today, do I need to sit down with a pen and paper and derive these derivatives?
Thank God, no. That is the beauty of the modern tech stack. We have something called automatic differentiation.
This is what libraries like PyTorch and TensorFlow do under the hood.
Exactly. When you write code in PyTorch, you don't tell it how to do the backward pass. You only define the forward pass.
You just build the graph of pipes and valves.
Right. And the software records every operation you do.
It keeps a log. First we multiplied, then we added, then we squared.
And because it knows the rules of calculus for each of those tiny steps, when you're done, you just call one magical function, usually loss.backward.
And the system automatically rewinds the tape.
It calculates all the gradients for you instantly.
So the black box has a black box of its own. We've automated the hardest part of the math.
We have. But, and this is why we're doing this deep dive, you cannot just treat it as magic.
Because things break.
They will break. And you need to know what's happening. When your loss turns into nan, not a number, or your model simply refuses to learn anything new.
You need to be able to ask, did my gradients vanish?
Is my learning rate too high? Am I stuck in a saddle point?
You need to understand the mechanics of the engine to diagnose the car, even if you didn't cast the pistons yourself.
That's a perfect way to put it.
That's great. So let's zoom out. We've gone from the neuron to the mountain range. We've walked downhill in 175 billion dimensions using a map derived from 17th century calculus.
It's quite a journey.
When you look at this whole picture, what's the big takeaway for you?
For me, it's a sense of awe at the unreasonable effectiveness of it all. We were using a simple algorithm, gradient descent, on a landscape so complex that human brains can't even conceptualize it.
It walks down a mountain we can't see in a universe we can't comprehend.
And yet it works. It finds the valleys. It learns to translate languages and diagnose diseases. We have built an engine that can navigate a world that is far more complex than the theory suggests it should be able to handle.
We built the engine with backprop and the chassis with the neural network. But an engine is useless without fuel.
And that is the next big topic. You can have the perfect architecture and the perfect optimizer, but if you pour sand into the gas tank, you're not going anywhere.
The fuel is data.
Data. Next time, we need to talk about why more data isn't always the answer, and why a smaller model with high-quality fuel beats a giant model with garbage fuel every single time.
I cannot wait to dig into that one. Well, that's it for this deep dive into the engine of AI. Hopefully the next time you see a progress bar training a model, you'll picture that blindfolded hiker stumbling their way down a massive dimensional mountain just for you.
One step at a time.
Thanks for listening. We'll see you in the next deep dive.